keel clearance. Little under keel clearance means more lift. The narrow space under the keel makes it difficult for the water to flow from one side of the ship to the other, so it is harder to push the ship sideways. A higher lift means a pivot point closer to the center of lateral resistance. For the same change of angle, the center of lateral resistance of a vessel with high lift will drift less sideways than a vessel with a low lateral resistance. This results in an apparent pivot point closer to the center of lateral resistance for a vessel with high lift than the vessel with low lift. We can see that the same effect is present when the ship has headway, first in deep water, now in shallow water, in this case 1 centimeter under keel clearance, which corresponds to about 1 meter with a real-size ship. The apparent pivot point is closer to the center of lateral resistance. Motion of the ship after the lateral force have been applied. The rotation effect. Let's take a ship-shaped body, free to move on an air cushion. Let's push it sideways with some anti-clockwise rotation. Now stop the force acting on it and watch the resulting movement. The center of gravity is moving to the right, and the bar rotates around it. The point that has no speed, having for reference the surface, is P, the apparent pivot point. When a ship is being handled at low speed, when the pressure fields on the hull are actually very low, it is mainly due to the rotation effect that the apparent pivot point seems to move astern if the vessel is moving astern and turning, and ahead if the vessel is moving ahead and turning. The other factor affecting it is the ship-generated sideways current. Let's consider a ship turning and moving ahead. The sweeping movement of the stern creates a vacuum which in turn drags a mass of water towards the quarter ship side. The outer ship side also pushes a mass of water away. We will call it the ship-generated sideways current. Let's now stop the force creating the turning movement. The ship, with its rotational inertia, keeps on turning, but the rate of turn will reduce due to water friction. The ship-generated sideways current, with its own inertia, will catch the stern and continue to push it sideways, while the forward part of the ship is in undisturbed water. This force, acting more or less sideways on the stern, contributes in moving the apparent pivot point more forward. All factors stated above have been explained separately. In real life, they all combine together with various intensities depending on conditions. Quantifying precisely the resulting effect for every specific condition is far beyond the best mariner's abilities. But understanding these basic principles and knowing that they fit with reality may be of some help in everyday ship handling. Some real-life observations and how they meet theory. The ship-generated sideways current has a lot to do in the stern seeking to go upwind ability of a ship going astern. The ship adrift is pushed sideways in a beam wind. Its motion creates a ship-generated sideways current. When the vessel is going astern, it pulls the aft part of the vessel out of the ship-generated current. The stern being now in an area of relatively undisturbed water, the rest of the vessel still in the local ship-generated current, a turning couple is created, bringing the stern upwind. As the stern is progressively directed into the wind, it gets out of and produces less ship-generated sideways current. Another force couple is developing. The component of the propeller pull, which is directed in the opposite direction of the wind, is increasing. It creates an arm lever of a length d between the propelling force and the center of windage. As the component of the force increases, when the stern is nearly upwind, the lever distance d decreases. It is why ships will normally find an equilibrium angle a little bit off the wind, especially for ships having large stern accommodations. Another demonstration of the sideways current. The ship is pushed sideways by a tug and its own azipod propeller. The ship creates a side current. A short kick ahead is given to get the bow out of the created current. The stern is carried by the current, causing a turning couple. This time with sternway. This phenomenon was described in 2001 in the text Unpredictable Behavior, example of a reason to reconsider the theory of maneuvering for navigators by Captain Max J. Van Hilten. Donkey, because it describes the behavior of a ship pushed sideways by a forward escort tug, turning against the tug directing force. Initially, the ship is moving ahead. The forward escort tug will start pushing in order to direct the bow to port. The tug pushing has the following effect on the ship: a sideways motion of the ship to port, a rotation of the ship to port since the force is acting forward of the center of lateral resistance. By this sideways motion, the ship is also displacing a mass of water sideways with her, pushing it on port side, sucking it on starboard side. As the ship moves ahead, the bow will float in an area of relatively undisturbed water. The stern instead will be affected by the ship-generated sideways current that has started to develop, causing a turning moment that will reduce the port swing and can even initiate a starboard swing. When the ship starts a starboard swing, the stern, due to the rotation, keeps on generating more sideways current than the forward part of the vessel, thus amplifying the turning moment. The rudder of the ship is kept amidship all the way. For those who believe that the tug's drag is the main explanation, I invite you to watch closely the next experiment. Here is a live example of this effect. Even without a tug, with a single pull from a string, the phenomenon exists. A force acting closer to the center of lateral resistance will have a quicker effect since it produces more sideways current.